quad of this is week 64 of the Perl Weekly Challenge. I kind of had a go earlier in the week solving the problems in APL. I realized an issue in one of my solutions today, so I fixed that in the minimum sum path solution. So maybe I'll be able to talk about my old one and now my new one. And then word break, I started looking into arrays and strings, and it turns out this was quite cool. Where did I find this? List sequences and arrays. So it turns out that Raku also has the membership function. They call it isElementOf, which is the same thing. So we have Perl Weekly Challenge. Now Perl, yeah, see, in APL you're kind of dealing with the text element by element. There is also the find primitive, which indicates a 1 at the beginning of the whole sequence being found. So one thing that we can do often is just ask, are all of the elements in the left found in the right? But that doesn't take account of if you had P, E, R, and L sort of interspersed in this string, then you'd still return a 1 in this case. Whereas the find primitive in APL, oops, I didn't mean that. You just want are any found, right? So this is are all of the elements of the left found in the right, and here are any of the whole subarrays in the left found in the right. I think, can we do this for multiple? Can we do membership? Well, yeah, exactly. It won't map across several like this, because it'll just do the whole of the left array as a subarray, which would be like a nested vector. Okay, anyway, that's tangent enough. Let's talk about my solutions before I ramble on for too long. Alright, so the first problem is minimum sum path, and it's quite involved, so I think I'll pop to the text editor in a moment. What I might do actually, so my solution from earlier in the week, I'm not gonna really run through it, but my idea was kind of a sort of like a maze searching thing. It's basically, it's a search problem. So you have to choose a sort of way of searching through the space of all possible paths for the one which has the minimum sum. And initially I was thinking to optimize for potentially large matrices. We'll start from the top left, and we'll literally just sort of have a little iterative finder that sort of goes right or down and chooses whether to go right or down based on whether right or down is a lower number, essentially. And in the example case given, that works to give you the correct answer. But if you have another matrix where you have, a local minimum might be part of a path that isn't the overall minimum sum path. I wonder if there's a good example I can give. I think I was doing something like 1, 2, say you could do 4, 3, 5, 1. One, I think. So in this case, your first step is going to go to the right, because the 2 is less than the... Well, we go back to the solution that does this. So we start in the top left, and then we look at the numbers in both of these steps, and we sort of choose the lowest ones. We'll go to the right because the 2 is smaller than the 3. And then out of these two, 5 or 4, we'll go to 4 and then down this way. And the sum of this path will be 1, 2, so that's 3, sorry, 7, 8, 9. But if we'd chosen a more immediately larger step initially, we'd have 1 plus 3 is 4, 5, 6, 7. We'd actually have a shorter or a smaller sum overall, but this nonsense algorithm won't find that because it only looks for a local minimum at each step, which is no good. But we'll keep that as a test for later. Let's look at what I did come up with. I think what we'll do, let's look at the minimum sum path of this one first of all. So we start with just a description. We're doing indices from 1, which ends up being slightly annoying. Like, I think my approach, because of this new approach, which is more of a find all of the paths that would be valid, that would take you from top left to bottom right. Find all possible paths. So in this case, it's right, down, right, down, right, down, right, down, right, or down, right for a 3x3 matrix. Then find all the values in those and find the minimum sum. So the way I've done this is essentially, because you only have 2 choices, down or right, I'm representing all of my paths as Boolean vectors, where 0 indicates going down and 1 indicates going right. And first thing we do is we find these path lengths. Right, so it's a 3x3 matrix, and so the maximum path length to get from the top left to the bottom right would be 2 in each direction. So the first number here indicates how many steps down, and then it's how many steps across. And the total path length is just the sum of those 2 numbers. Then, since we're going to be representing all of our paths as binary numbers, what's the maximum number that it could be? And this is basically, it could be down or right, which is represented as 0 or 1. And the maximum sort of binary number representing a valid path would be this number, which represents sort of right, down, 1, 1, 0, 0. It might be easier to demonstrate with a non-square one. So if we start by that, so instead of the test case, let's do a 4x5 reshape, and that's 20. Okay, so if we look, we have this matrix. Our directional path lengths are 3 down and 4 across. All combinations will have those. So even if we like twist around in the middle, it ends up being 3 steps down and 4 steps right, no matter what. That's what allows us to determine our maximum path number, 120. And in base 2, that's just 4 steps to the right and 3 steps down. So then we have our possible steps. 1, 0 indicating down, so 1 step down, 0 steps right, or 0, 1, 0 steps down, 1 step right. So those are our steps. This is a little bit involved, but there's not much to it. I can't remember how I settled on this logic, but I figure it works. So our smallest path number will be 3. Our smallest path number will be 3, but this is basically 0.000.111, which is binary for 3, and that represents going... okay, but this is potential path numbers, just to make sure we get all of the stuff in range. Oh, our smallest actual valid path number would be 15, I think. Yep. 0.0.1111. Okay. So we then find, let's just take the first 5 of these. We find all of these binary numbers going from our smallest one that we think of, which is almost definitely outside of the range. In this case, it should have been 15, I reckon, rather than 3. But it doesn't matter if you find a few too many. Better safe than sorry, I suppose. So it finds all of these where each row represents a sort of path. Some of them aren't valid. Most of them aren't valid. We find the valid ones by asking, if I sum across, which one of these have 4 ones? Right, zeros represent going down, which there'll be 3 in the maximum case, and 1s represent going across, and for valid paths there should be 4. So it's easy to verify which are the valid paths, and then filter. So now these are all paths where 0 represents down, 1 represents right, that will take you from the top left to the bottom right. So these are all the potential paths. Then we're going to grab our step combinations like this. So this is saying for each path, which contains 7 steps, that's the path length. For each of these paths, we need to now find the path values. So the first thing we'll do is, since each of these represents steps, to get the actual set of indices, we're going to do a cumulative sum down each of our matrices. So rank 2 is rank 2 arrays, cumulative sum, oops, not PL, sorry, these, right? And then we need to add the origin. Okay, and so this is basically saying for this path, I might be doing something slightly wrong here. So split these. So now each row is a path. We can grab the values like this. Sum. These are our 7 steps. Okay, never mind, this is right. So for all our valid paths, what are the path values? If we look, we found 35 ways through this matrix. Right. And then to sum them, we just sum them. To find the minimum, we just find the minimum. Here we're going to find the index in our array of paths. In our array of 35 paths, which is the index of the lowest path, MSPI. And actually, if you look at the sum PV, and we do MSPI squad that, we should find the smallest sum there. So number 35 ends up being the smallest sum. Strange. Right, then similar sort of thing. Those path indices from before. In fact, we could grab the path indices from here, I think, instead of having to generate them again. Oh, but this is only for the one. So then we could use indexing. Hold on. We get as far as this. And we call these our path indices. MSPI squad PI. Right. Oh, and that should be the same as our path indices. Oh, except we're missing a 1, 1, but that's it. Yep. So it'll save us a bit of extra computation if we make sure we set the path indices in there. And for clarity, valid path indices. Okay. Oh, yeah. And then our minimum path indices. Oh, that's the issue. Well, we can tack 1, 1 onto minimum sum path index, indexing into our path indices. Okay. So we'll go back here. These are our path indices and our path values. And now realizing why do I have 1 comma? Because I'm assuming the top left starts with a 1, but that's not right either. Okay. Yeah, this 1 comma should probably be pick omega. Okay. There was the reshape right. Okay, well, since dialogue crashed just now, I'm going to skip through all this using the normal example. Hey, you did it. So the crux is, we're doing a kind of breadth first search. We find all the possible paths, find all those values, and then find the sums, and then since our path values and our path indices and everything, all of these arrays are in a structure such that they all have the same 35 major cells. So, or rather, they all have they're all arrays which are collections of paths. So they all have the same length. So once I find the minimum sum path index, I can use that to index into all of my other arrays. I could use it to index back into the path values from which I found the minimum sum path index, but that's obviously pointless. But yeah, just keeping all of your data in this regular structure makes stuff fairly straightforward. So you can see here in the example, we get, an output. The sum is 21. Here are our indices in index origin 1, and here are the values. And if we want to do our test, which was something like 1, 2, 1, 1, 1, 1, 2, 4, 2, 5, 1, 1, 1, 1, I think. So here in my old algorithm, in fact, replace the other 2 with the 3, it's even clearer. In my old algorithm, it would have gone this way: 1 to 2, 2 to 4, then down. returning a path of some 3, 7, 8, 9. The new one correctly identifies this path 1, 3, 1, 1, 1 with a total of 7. So yeah, that's minimum sum path in APL. And right, let's look on word break. So word break is some array of words and a string. And the example here is Perl Weekly Challenge. And the string, and the list of words is Weekly Challenge Perl. And we find it. And if we change this, then I break it immediately. Yeah, never mind. I clearly didn't finish solving that one. That one, this week's not been very interesting from me. Thanks for watching anyway if you did. We'll try again next week.